are represented in computers. And we start with a look back at what round of errors are. Now, this has been covered in the previous class. So this is just covering old ground in order to have some continuity. Now, if I ask you what round of error is, what your answer is going to be? Any answers?
Sir, after a certain value, we generally stops taking values, and like 1.3333, then we take 1.34, something like that.
Okay. When a real number cannot be, say, represented exactly, and we have to truncate the number after a certain number of digits. That is what you are saying. And
Yes, sir.
this is when the round of error arises. So we can define this as an error created due to approximate representation of numbers. Now keep in mind that computers have finite memory and consequently finite space to store or represent numbers. So it is quite natural that certain numbers cannot be represented exactly and can only be approximately represented in the computer memory. Such type of numbers are just a moment. As I was saying that certain numbers can only be approximately represented in computer memory, computer storage. What kind of numbers? Numbers such as recurring decimals, as one of your friends just now pointed out, that 0.3333 like that. So 1/3, 2/3, and certain irrational numbers as well. For example, pi or √2. These cannot be exactly represented. So here, let us say we have a real number x and its corresponding computer representation, or rather the floating point representation, is given by FLX. These two numbers, that is the real number x and the floating point representation FLX, they have the similar form, but the only difference between them is that x has infinite number of digits if required after the decimal point, whereas the floating point representation has finite number of digits after the decimal point. By the way, this floating point representation of the real number is also known as machine number in some cases. As these two are not same, obviously there is some gap between the two, and this gap is referred to as the round of error. The mathematical expression for the absolute and relative round of errors are given on the right hand side. I'm not going to go over them as we have already discussed these topics in the last class. But what we should pay attention to here is that how do we get a finite number of digits after the decimal point from the infinite string of digits? There are two ways in which it can be done, and the first of the two ways is known as chopping. Simply chop off the numbers after a certain digit. We drop the numbers, let's say, after k number of digits. That is known as chopping. Let's take an example here, or let's explain this with the help of this arbitrary number, let's say 0.d1, d2, like that, we continue up to dk, dk plus 1, and it goes on, multiplied by, say, 10 to the power. So that is a representation of a number. By the way, this is a decimal number. We have not yet gone into the realm of binary representation. So what is done in case of chopping is that after, say, k number of digits, we drop these values. By the way, here d1 is given by this, whereas di, I varying from 2 to, say, infinity, this is given by so anyway, in case of chopping, we discard these numbers after the decimal point, after a certain number of digits, and we obtain this as the approximate representation. So this will be FL X, whereas the original number was X. So that is the first way of doing the things, getting a floating point representation. The second is called rounding. In rounding, what we do is we look at this digit, that is dk plus 1. If this is less than 5, if dk plus 1 is less than 5, then we simply chop. That means what we did in chopping, that is repeated. So digits after kth digit are discarded. Simply discard. There is no change in the first k digits. However, if this dk plus 1 is greater than or equal to 5, then we add 1 to the kth digit. So dk becomes dk plus 1. Quite simply, if you consider the case of, let's say, 0.666 like that. So we are considering the case of 2 by 3. It's a recurring decimal. After 4 digits, if you chop, it is going to be 0.6666. But after 4 digits, if you decide to round, then this becomes 0.6667. So if the kth digit is k plus 1th digit is less than 5, then we round down. And if it is equal to or more than 5, then we go for round up. I hope this is clear. So there are two ways in which you can cut down on the infinite number of digits after the decimal point to a finite number of digits, and these two options are chopping and rounding. But the thing is, whether you do chopping or rounding, you are going to introduce some approximation and hence some round off error is going to come. Here the examples I have provided is in decimal system for better understanding. But computers do not understand decimal systems. So obviously, computers would be using a base 2 system or a binary system where they are using binary floating point number notations. So we have to consider this. That is why the note that I have circulated regarding the binary representation and the mutual conversions between binary and decimal and vice versa is very important. You should go through that. So this actually underlines that we need to understand round of errors, and in order to do so, an in-depth discussion regarding the representation of numbers in computers, in computer memory, is necessary. Computers store numbers as floating point numbers, and hence we need to talk about floating point representation of numbers. But before we move on to that, we must first of all acknowledge that there are various different number representation systems. One that we are absolutely familiar with, and the representation which comes most naturally to us, one that we learn and internalize since our childhood, is the decimal number system. That is the base 10 system. It uses 10 digits, obviously, 0 through to 9. And a number is represented, whether it's an integer or a fractional number, doesn't matter. It is represented as a sequence of digits. Each place in this sequence of digits correspond to some multiples of powers of 10. Here is an example of a decimal system number representation, but I don't think an explanation of this is necessary. We all know how it works. There are other number systems as well. For example, there is octal number systems. It's a base 8 number system. We also have hexadecimal number systems, which is base 16. Now, in case of base 8, we have digits, 8 digits, of course. So starts with 0, goes up to 7. What happens in case of base 16? We cannot cover 16 with only the digits. So we go from 0 to 9, that's 10. What happens after this? Anybody knows?
So
So we'll use the first 6 letters. So A, B, C, D, E, and F. So here A corresponds to what?
10.
10, 11, 12, 13, 14, 15. So this is the base 16 hexadecimal systems. But right now, we are only interested in the binary system, which has base 2. And we are interested in this because
স্যার এটা 10 কি করে হবে 11 হবে তো
yes,
মানে এটা তো 11 রিপ্রেজেন্ট করবে না কারণ 0 টু
no. It starts with 0. How do we count? We count from, say, decimal system 0, 1, 2, 3, 4 up to 9. Then it becomes 10. 10 means 1 unit. So here the unit is 60. You go from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Then 10. 10 is A. 11, 12, 13, 14, 15. That is altogether 15 digits. The 16th one becomes 1 unit again.
ওকে স্যার
Okay. So as I was saying, that Why we need to study binary systems in much more detail? That is because the computers use binary representation. Here we have only two digits, 0 and 1. Whether it is a fractional number or an integer, it is written as a sequence of zeros and ones. And here also, each place in this sequence, this sequence of zeros and 1 corresponds to multiples of powers of 2. Please go through the note to have a better understanding of how this representation works. But here is an example. You can see that a binary number 10011.101 is represented. By the way, here I would like to mention that the point here is known as a binary point. In decimal system, we use the decimal point. In case of binary system, there is a binary point. You can see how this binary number has been converted to a decimal number. We look at where the ones are. Let's identify those positions where ones are located. So we have in the 2 to the power 4th place, 2 to the power 1 place, and 2 to the power 0 place. That means we are talking about before the point. So 2 to the power 4 can be added to 2 to the power 1 and 2 to the power 0. That gives you the integer part of this number. And this comes out to be 19. What about the fractional part? Here we have negative exponents. So 2 to the power minus 1, 2 to the power minus 2, like that. Here also we add up those positions where the ones are present. So 2 to the power minus 1 plus 2 to the power minus 3. The first one corresponds to say 0.5. The third one corresponds to 0.125. Whereas the second one has got 0 in its place, so that becomes 0 altogether. If we add all of these together, we get the decimal number as 19.625. The process is pretty trivial, and once you have worked out a few examples, you will get the hang of it. Obviously, the opposite needs to be done sometimes as well. That means the going from the decimal to the binary representation, and that has also been explained in the note that is circulated. Please go through that. Here, another thing that needs clarification is the terminology of bit. What is a bit? Each binary digit, 1 or 0, is called a bit. This is a short form, you can say, of the binary digit. Bit comes from that. So each of these zeros and ones would be referred to as a bit. So we know that computers use binary system. But what kind of notation do they use? They use scientific notation, and that is known as the floating point representation. Why do we use such a notation for computers? That is because it is able to represent very large as well as very small numbers, real numbers of course, with the minimum amount of space. That is why we have gone for this floating point representation for computers. Now let's talk about this floating point representation in a bit more detail. Here, a number in general is represented using a mantissa, which is also called sometimes significant, and with respect to some fixed base and an exponent. So if I write this out in terms of a mathematical expression, number becomes equal to significant multiplied by the base to the power of exponent. And that is what is shown on this green rectangle. X is equal to f multiplied by beta to the power e. Here f is the mantissa or significant, which can be positive or negative. This is basically a digit string, a string of digits of a given length in a given base. Now here I have mentioned given length, but if required, this length can go up to infinity. It can be of infinite length. It is also important to remember that this length of the significant or length of the mantissa is directly related to the accuracy of the number being represented. So you can see here that the length of the significant determines the accuracy to which numbers can be represented. So this length is very important. What about the exponent? It is a signed integer. It basically gives you a range of numbers depending on what exponents can be considered. So it modifies the magnitude of the number, whether it's a very big number or a very small number. And finally, the base is used for scaling. We know that beta is equal to 10 for decimal systems and 2 for binary systems. We are at the moment interested in the binary system. The importance of the exponent and the base, of course, can be explained in terms of the range of numbers that can be represented. You may need to represent very large numbers, say universe level numbers, astronomical numbers such as distance between stars or distances between galaxies. So you can have 10 to the power 10, 10 to the power 20. These sort of numbers are huge numbers, but they can be represented using similar amount of space in computer memory. On the other end of the scale, you can go for subatomic numbers, subatomic level numbers, that mean distances between atoms, very, very small distances. So in that case, the exponent can be modified in such a way that the same space can be used to represent such very small numbers. So using the same amount of space, you can go for a huge number as well as a very small number. Only thing is that the exponent goes from positive to negative. Instead of considering, let's say, for example, to the power base to the power 20, you consider base to the power minus 20. One is a very big positive number, one is very small positive number. So that is the beauty of this floating point representation. But do consider, at this point, we have not yet introduced any kind of approximation. This representation that you can see is basically an accurate representation. Any real number accurately represented by an infinite sequence of digits. If we consider binary representation, then of course this base beta can be replaced by 2. We have written out the significant or the mantissa in this form. So it is a string of digits. In case of binary, digits are 0 and 1. So this is basically a string of zeros and ones. So we can write this as fi equal to 0 or 1, where I goes from 0 to infinity if required. Certain numbers may not require infinite sequence of digits, but some may need infinite sequence of digits, and if required, it can go up to that. Because we are still now talking about the real number x. This is the integer exponent, also represented in binary. Remember that whatever we are using as the system for the significant, it has to be reflected in the other parts also. You cannot have a representation where the significant is in binary form, whereas the exponent is in some other form. It is in decimal form. That is not allowed. So there has to be consistency in the number system. If the significant is in binary, obviously the exponent has to be binary as well. And remember also that the exponent is always an integer value. But at this point, we talk about normalized representation. Have a look at this particular term, F0, which is to the left of the binary point. This is known as the most significant bit. In short, this is written as MSB, most significant bit. This most significant bit, which is to the left of the binary point, can have two possibilities. It can be 1 or it can be 0. If F0 is equal to 1, then it is known as a normalized representation. And the numbers used in normalized representation are usually referred to as normal numbers. On the other hand, if this most significant bit, F0, is equal to 0, the numbers are called subnormal numbers. And this is known as a denormalized representation. In this class, we will only be looking at normalized representations and normal numbers. So we will consider F0 as one exclusively. We will not consider the case of F0 equal to 0 for this class. So considering normalized representation and F0 as 1, the decimal value of this mantissa is, of course, 1 plus F1 by 2 plus F2 by 2 to the power 2 plus F3 by 2 to the power 3. Like that it will continue, possibly up to infinity. Again, I remind you that this is x we are talking about. This is the real number. As yet, no approximations. But of course, now we have to go from the real number to the computer representation of the real number given by FLX. This is an approximate representation, obviously a floating point representation. This is going to be similar in form to the real number. So we can write FLX as sine of x multiplied by, now we can see that the most significant bit F0 has been replaced by 1 here. Notice the 1. So this is a normalized representation. This is a normal number. So 1, then binary point, then this digit string F1, F2, F3, it continues up to Ft. Now this is where the approximation comes into effect. The previous one, the real representation, it could have gone up to infinity. But here we are truncating the digit string after t number of digits. This could either be done through chopping or rounding, whichever is applicable. And then after the mantissa, we have the base 2, raised to the power e. So that is the exponent. And this t is, of course, fixed in advance depending on the computer architecture. We can also write the same expression like this. Sine of x is replaced by -1 to the power s, where s can have either a 0 value or a positive value, depending on the sign of the mantissa. So if s is equal to 0, this becomes a positive number, and if it is 1, then the number is a negative. So now let's see what kind of space needs to be allocated in the computer memory. You need space for the mantissa, of course. You need space for the integer exponent and also for the sign of the mantissa. So some finite number of bits must be allocated to store these parameters: the mantissa, the exponent, and the sign of the mantissa. So let's point them out one by one. So first of all, storing the fraction part of the mantissa in memory requires t bits. Starts with 1, ends with t. Here, notice that I have mentioned storing the fraction part only. Why the fraction part? The other part, that means the most significant bit to the left of the binary point, is always 1. So this 1 can be implied or it can be hidden. When you are going for a calculation, this 1 can be added up. But in storage, we will keep only the fractional part of the mantissa in t number of bits. This has an added advantage also, that we do not waste a bit for storing the 1. Because it is implied, all the bits, all the t bits would be devoted to storing the t bits of the fractional part. As a result, the accuracy of the number increases because we are getting more number of bits, larger number of bits to represent the fractional part of the mantissa. Next comes the sign of the mantissa. It is quite straightforward. We require a single bit, which could be either 0 or 1. And finally, we have the exponent. This exponent e also needs to be stored in a fixed number of bits. So let us look at this in a bit more detail. This is the same expression as the previous one. What we have done is that we have interchanged the location of 2 to the power e and the mantissa. Why it is done, it will become clear shortly. But before that, let me just also say that the decimal value of this floating point representation can be calculated using the expression shown here. So you have FLX equal to -1 to the power s, which could be 0 or 1, multiplied by 2 to the power e, the exponent, multiplied by 1 plus f. Here is the one that was left implied, that is added up over here. And f is the fractional part, which is given like this. So here we can write f as f1 by 2 plus f2 by 2 square. Like that, we can go up to ft divided by 2 to the power. Depending on whether these Fi's, that is F1, F2 going up to Ft, they are zeros or ones, I can calculate a value for F, which can then be added to 1 to get the actual value of the mantissa, and then it is multiplied by 2 to the power e. The sign needs to be taken care of as well, and that is how you get the decimal value of this approximate representation. You had the real representation x. Now here is the decimal value of FLX. So in terms of a numerical problem, if you are told to calculate the round of error, whether absolute or relative, you can do it through these expressions. Now let us see how these different parameters, the sign, exponent, and the mantissa, are stored in computer memory. Let us consider this graphical representation of which, let's say, this is analogous to the to a particular location in computer memory, and this sign could be stored here. It requires a single bit. Then comes the exponent, which is going to be stored in this red box over here. One thing to be very clear about here is that this sign is not the sign of the exponent. The sign belongs to the mantissa. Although the exponent appears just after the sign here does not refer to the sign of the exponent. Sign of the exponent would be taken care of separately. The sign belongs to the mantissa part, which is stored in this blue rectangle shown over here. Now, obviously, these spaces, these you can say spaces denoted by different colors here, would be made up of different bits, different number of bits. So we can go for a representation as shown here. Obviously, the sign bit is a single bit, so that takes care of that part. Now, the exponent, let's say we have m number of bits to store the exponent. So it starts from E1, goes up to EM. The integer exponent, including its sign, would need to be represented within these specific number of m bits. Then comes the mantissa. In this mantissa also, we have t number of bits. In this t number of bits, we have to represent the mantissa. So the total number of bits required for this representation, if we start with B01 on one end and go up to Bn-1 in the other end, we have total mn number of bits. And this n is made up of the bits required for sign, the exponent, and the mantissa. So it quite clearly means that n is equal to 1 plus m plus p. This is known as the n-bit representation of a floating point number. But remember here that we have not yet attached any specific values to it. So what should be the value of m, or what should be the value of t? Whether m should be greater than t, or is it the other way around? T should be greater than it. Whether the exponent should be given larger space, or the mantissa should be given larger space.
So the mantissa.
Mantissa, obviously, how would you?
We will come to that, of course. We'll definitely come to that. And you are quite right that there is the mantissa which has the larger space, but it obviously there is a trade-off between the two. We'll explain that. So if n bits are available to store floating point numbers, certain points need to be taken care of. First of all, this is straightforward. There is no complications or ambiguities. Here we have one bit it would be 0 for plus and 1 for minus. Next comes the question, how many bits to be used to represent the mantissa, followed by these two very pertinent questions, how many bits to be used to represent the exponent, and finally, how to represent this sign of the exponent. The sign of the mantissa is already taken care of. We need to think about the sign of the exponent. As I said, the first point is already discussed. So we will move on to the second point. How many bits to be used to represent the mantissa? I have already mentioned that the larger the number of bits, more accurate is the representation. Another way of saying that is that more number of correct digits after the decimal point would be obtained if you go for larger number of bits representing the mantissa. So you can say that the number of bits to be used for the mantissa is determined by the number of significant decimal digits required in a computation. Whether you need the number correct up to 5 decimal places or do you need it correct up to 12 decimal places, there is a difference. If we need it only correct up to 5 decimal places, then obviously the mantissa would be smaller. But if you need correct up to 12 decimal places, then it has to be a larger mantissa. And corresponding to that, larger number of bits need to be reserved for the mantissa. And this is where the advantage of the normalized representation is realized. The normalized representation is basically adopted to increase the accuracy. The most significant bit, that is the leftmost bit, one to the left of the binary point, is always 1. That is the normalized representation. And as this is always 1, this bit is always 1, then the fixed leading one can be removed from the memory, and in doing so we have saved 1 bit. So we can increase the length of the fractional part of the mantissa by 1 bit, and that is the advantage of the implied or hidden 1. As already mentioned, in computer memory, only the fractional part of the mantissa is stored, and it increases the mantissa by 1 bit. This extra bit ensures that the number of significant digits in the mantissa would increase. So that is all about the mantissa. Next, we go to the exponent. Now, what is the function of the exponent? The function is that if we go for more number of bits, we have larger range of numbers. Larger range of numbers can be represented. But here we have to take care of the sign of the exponent also. We can do it in the same way that we took care of the sign of the mantissa. That means we can reserve 1 bit for sign. So the exponent may be represented in sign magnitude form. But that reduces the number of bits reserved for the magnitude of the exponent. Not by much, of course, but there is a problem that comes out of this representation. That is, if we save 1 bit for the sign. This representation causes a case of duplicate zeros, a positive 0 and a negative 0. You will see that happen in case of the mantissa as well. But in order to avoid that, in case of the exponent, that means to avoid having two different types of 0, a positive 0 and a negative 0 exponent, we go for an excess representation or a biased representation. To avoid using that 1 bit for sign, the value of the exponent is entered with a bias. This is known as the excess representation or the biased form. What is done is that we add something to the exponent and make it a positive number. This is basically analogous to, say, changing the origin of a coordinate system. So what we do here is a constant value, which is obviously called the bias, is added to the value of the exponent. So exponent becomes equal to the actual exponent plus the bias. So if exponent is represented by capital E, that means the biased exponent is capital E, then capital E is equal to small e, which is the actual exponent, plus the bias. I think this needs to be explained in a little bit more detail, and that is what we'll do in this slide. So we will use the total m number of bits for the exponent. No separate bit for the sign of the exponent, as it will be taken care of by the bias representation. And the bias representation, as you can see here, is, as explained in the previous slide, is capital E equal to small e plus b. Here capital B is the bias. Now if we have m number of bits for representation of the exponent, how many numbers can we represent? We have total 2 to the power m integers. And the range that we have is starting with 0. That corresponds to all zeros in this exponent here. All the m bits in the exponent would be 0. And it goes up to 2 to the power m minus 1. That means all the bits here would be equal to 1. So that is the total range. Starts with 0, ends with 2 to the power m minus 1. Let's say this is the graphical representation of the range. Now, if I just say, as I told you, that if I shift this 0 to somewhere around here, so with these positive numbers, I'll be able to represent some negative numbers also. One-to-one correspondence would be there. Let's say if I write 0 over here, that actually indicates minus, let's say, n. That can be done very easily with adding this bias. So if I have a negative number minus n, how much do I need to add it to make it 0? I have to add plus n. Plus n becomes the bias. Obviously, we can calculate the exact amount of bias that is required if I want to have half of this range as negative exponents and the other half as positive exponents. So this is the midpoint. That is the midpoint. And the midpoint is, of course, 2 to the power m minus 1 divided by 2. Here, we have to consider the integer part of it. Why? Because 2 to the power m is an even number. 2 to the power m minus 1 becomes odd. If you divide it with 2, fractional number with 0.5 in the fractional part. So we drop the 0.5, we chop it off, we only take the integer value. So that is the midpoint of this range. And that value, integer of 2 to the power m minus 1 whole divided by 2, that gives us the bias. What we'll do is we will subtract this bias from this entire range, throughout this range. So obviously, 0 becomes minus bias because I have subtracted bias from this 0. So there is minus bias on one end, and the other end, that means 2 to the power m minus 1, that also has got bias subtracted from it. Now the range of exponents with m bits becomes minus bias, which is a negative number, starts from there, increases, goes to 0. There is only one 0 representation here, and then moves to the positive part. How far it goes up to? It goes up to 2 to the power m minus 1 minus the bias. That means this becomes the range. Those are the exponents that are represented. But in the computer memory, which number is going to be stored? The numbers that are going to be stored are these numbers. As I said, there is obviously one-to-one correspondence. So if in this exponent part, if 0 is stored, if I see that 0 is stored here, I automatically immediately know that it is referring to, in fact, a negative bias, negative exponent equal to minus bias, where the bias value has already been calculated using this expression. So that is how the negative and positive exponents are taken care of in floating point representation.
স্যার তাহলে একটা বিট বাঁচাতে যে মানে অনেকটা রেঞ্জ চলে গেল না ওইদিকে, না এক্সপোনেন্টটা অত লাগে না, মানে 2 টু দি পাওয়ার m মাইনাস 1/2 থেকে 2 টু দি পাওয়ার m মাইনাস 1 ওই নাম্বারগুলো তো পাবো না নাকি স্যার?
না, ওগুলো আমি পাচ্ছি।
মানে ওটা তো তাহলে কমে
m minus 1 থেকে 2 to the power m পর্যন্ত এই পার্টটা পাবো না। বাট look at what you have gained. You have gained the other side, isn't it? If we go from 0 to 2 to the power m, you can only represent very large numbers. You cannot represent very small numbers, is it?
Yes, sir.
যদি আমাকে স্মল নাম্বার রিপ্রেজেন্ট করতে হয়, তাহলে আমাকে তো নেগেটিভ এক্সপোনেন্টের প্রভিশনটা রাখতে হবে। সেটা যদি না থাকে, আমি শুধুমাত্র পজিটিভ নাম্বার রিপ্রেজেন্ট করতে পারি। সরি, পজিটিভ নয়, শুধুমাত্র লার্জ নাম্বারস রিপ্রেজেন্ট করতে পারি। So it is better to maybe not have too many large numbers, but also have very small numbers in the range. এটা ক্লিয়ার হয়েছে কি?
Yes, sir.
It's a matter of choice. Okay. So we have established that what are the things that need to be taken care of in the floating point representation. But here comes a question of trade-off, optimization. If I allocate more bits to the exponent part, I make the exponent larger as compared to the matrix, because I have in total n number of bits. I cannot change that. N is fixed. Out of that, 1 bit is taken up for the sign of the mantissa. So now I have n minus 1 bits. In that, I have to represent both the exponent as well as the mantissa. If I increase the bits for the mantissa, then it widens the number representation range, but it cuts down on the accuracy of the number. Vice versa, if I increase the mantissa part as compared to the exponent, then I increase the accuracy of the numbers, accuracy of the representation, but I cut down on the range of numbers that I can represent. So there needs to be a trade-off between them. I have to select a suitable value for the exponent, that means number of bits for the exponent m, and the number of bits for the mantissa t. The good news is that this is all standardized. That means you do not need to decide. It is already decided. The bit allocation for floating point number representation is standardized by IEEE. So next, we will look at the IEEE standards. At this point, let me ask if there are any questions. I have covered quite a bit of material here. Not difficult, but a lot of material has been covered. So are there any questions regarding any of the slides, any topic that we discussed? No questions?
মানে ম্যান্টিসা পার্টটা ওই আমরা 1.1 F1 F2 ওরকম নিচ্ছি, তো ওটা একটা অ্যাড মানে একটা তো পরে সেটা তো মেমোরি অ্যালোকেশনের ব্যাপারটা, মানে ওটা আমি 2 পয়েন্ট নিলে বা 3 পয়েন্ট নিলে মানে একই কেন নিচ্ছি মানে ওরকম?
It is binary representation, remember that. বাইনারিতে আমার ডিজিট হচ্ছে 0 আর 1.
ও মানে ওটা একটা বিটকে বলছে?
হ্যাঁ, that's the bit. As I said, it is the most significant bit, left side of the binary point. So only two possibilities, 0 or 1.
Sir, how does the biasing is done, sir?
A bias, let's move forward now, and I will show you an example. After the preliminary discussions about the standards or formats, standardized formats, we will look at a single precision format. There, I will show you how the bias is calculated. I think that will probably make it just a little bit more clear. If not, then we can discuss about the bias again at the end of the class. Okay?
Okay, sir.
So let us now go back to the presentation again. So let us now talk about the IEEE floating point standards. The floating point standards, floating point representation of numbers, were started during the mid-1950s. So that is the time frame when computers started to have floating point representations. But at that point of time, different manufacturers of computers had their own representations. There was no uniform representation or standardized representation. The problem with that is that the portability of the say computer programs suffers due to that. That means a program written on one computer may not run or give some error-prone results if it is run in a computer of a different manufacturer. For example, let's say you have, as a student, you have a computer with Intel chip, Intel motherboard, maybe Intel i3. So the number format for that would be different from a computer which is manufactured by some other manufacturer. Let's say your friend has a Mac. So for that the numbers storing format or representation of the numbers, real numbers in that computer would be different. So if you write a program and give it to your friend, he will not be able to run that program in his computer, in his Mac, using the other format. It will give errors or error-prone results. The results are not going to match. So it is quite a problem. But during that time, it did not cause such problems because computers were not that popular and their usage was limited. But from the 1980s, with the advent of personal computers, they became more popular and their usage increased exponentially. So at that point of time, it became necessary to have some standardized format. So Institute of Electrical and Electronic Engineers, they constituted a standardization committee, and the first standardized system of representation of numbers was floated in 1985. That is the year when all the computer manufacturers accepted these standards, which were known as IEEE Binary Floating Point Number Standard. It is designated by the number 754 followed by 1985. That means the year when it was floated and accepted by the computer manufacturers. Now, there is no difficulty in portability. All computers, whether it's a Mac or an Intel-based computer system, they will have the same format for floating point number representation. So what do these standards have? What do they say? They basically define the number representation format, the format that we have till now talked about, that is given by the standards. Also, it talks about how many bits are to be reserved, how many bits are for the mantissa, how many bits are for the exponent. It also talks about different kinds of rounding rules, certain operations, and exception handling. Exception handling means suppose you have a 0 by 0 in your computations or a negative number under root. So how these exceptions are going to be handled, that was also standardized. That means these exception handling is also uniform throughout all computers. So these were the formats that were introduced, and these standards were later on revised in 2008 and also in 2019, but the main framework of these standards remains the same as published in the 1985 standards. What happened in later standard where some minor modifications or some minor revisions were done, but no major changes have come about. The 1985 standard, the original standard, proposes or gives two different formats to represent floating point numbers. One is a 32-bit format, the other one is a 64-bit format. The 32-bit format is known as single precision format, and the 64-bit is known as double precision format. Later on, in 2008, two other formats, half precision and quadruple precision, were floated. That is 16-bit half precision and 128-bit, which is the quadruple precision. These formats have also been defined in 2008. But we are interested only in the single precision and the double precision formats, that is 32-bit and 64-bit respectively. In this 32-bit single precision format, 1 bit is reserved for sign, 8 for exponent, and 23 for mantissa. That is fixed. There is no way of changing. So as you can see, it starts with B0 ends with B31, that means total 32 bits. B0 is obviously sine. B1 to B8, that means 8 bits for exponent, and the mantissa is stored in the consecutive 23 bits. What about the 64-bit double precision format? Here also sine is 1 bit. Now the exponent becomes 11 bits. After that, the mantissa has 52 bits. Obviously, the double precision format is going to have much more accuracy compared to the single precision, just because of the length of the mantissa. We will look at the 32-bit single precision format in a bit of detail. Now, I'll leave the 64-bit double precision format for you to go through. I'll give the, say, skeletal framework of the important points in that particular format, but the calculations required are to be done by you. So, a sort of homework kind of thing. It's not an assignment that you need to submit, but do go through it by calculating through hand calculations. But obviously, the steps required, the procedures are very much similar. So it should not be a problem. So let us look at the 32-bit format, the single precision format. Here, the sign bit, it's given really 0 or 1, depending on whether the number is positive or negative. I would mention again here that this sign corresponds to the sign of the mantissa, not the exponent. The exponent is going to be taken care of through the bias format. There is no separate bit reserved for the sign of the exponent. Here, the value of the bias is 127. Now, how do we arrive at that number?
2 to the power 8 করলে 255 হচ্ছে, তো সেটাকে হাফ করলে তো এটাই আসবে, মানে ইন্টিজার পার্টটা।
2 to the power 7
Yes.
করলে তো মনে হয় 1 কত 27 28 আসে মনে হয়।
2 to the power 8 minus 1. That is what we have to consider.
Yes, sir.
2 to the power 8 minus 1. 2 to the power is 8 is 256. This becomes 255 divided by 2. So that makes it 127.5. You drop this part. So integer part of this 2 to the power 8, 2 to the power m minus 1 divided by 2 gives us 127. Now, please consider one thing here. If I had reserved 1 bit for sign over here, this bit, let's say I have reserved that bit for this sign, 0 or 1, depending on whether it's positive or negative. So I will have how many bits over here?
7
7. So
এক্সপোনেনশিয়ালি কমে যাবে।
2 to the power 7 means
2
how
to the
much?
power
128.
128।
128. So 128 positive. If I have a 0 before that, 128 negative as well. So total of 256. Keep that in mind. So 256 exponents, positive as well as negative, can be represented here. Let's see what happens next. Now we go back to our biased format, that is without the sign bit. We have seen that the bias value is 127, and the range of E, that means integer value that is stored in the 8-bit exponent. That means the biased exponent that varies from all zeros to all ones. 8 zeros consecutively, 8 ones consecutively. And those are in decimal form 0 and 255. So this is the range. What is the bias? 127. I can represent total 256 integers starting with 0 to 255. If I take out the bias from that, then the range becomes minus 127, 0 minus 127 becomes minus 127, and 255 minus 127 gives us 128. So that is the range. That is the range of the exponent small e. How many numbers I can represent here? 256. So I have not saved anything. Means if I had gone for a sign bit followed by 7 bits for the exponent, I could have represented 256 of them. Here also I can see that I can represent 256. So where is the difference? Why should I go for this biased exponent? The problem here is that the problem in this representation, that means signed representation, is that there would be 1 plus 0, there is 1 minus 0. Consider the case when this first bit of the exponent is 0 followed by 7 zeros. So that is the positive 0. What about the case when the first bit of the exponent is 1 followed by 7 zeros? That is a negative 0. So we are using two different representations for the same number. There is no difference between a positive 0 and a negative 0. So that is where it saves us 1 bit. And to avoid the confusion regarding the positive 0 and the negative 0 in case of exponents, we go for the biased representation. But in this biased representation also, minus 127 and 128, that means the two extremes of this range are reserved for special numbers. So if I go for this table, you'll see that the range of integer exponents in binary are represented in the first row that starts with 8 consecutive zeros. That gives us a value of 0 in decimal. The exponent here is minus 127. That is a special reserved place. We do not use this. On the other end, where we have 8 consecutive ones, that gives a decimal value of 255 and an exponent value after taking out the bias of 128. This 128 is also reserved for a special representation. What is that representation? We'll come to that later. So it means that the range of small e, the exponent, is minus 126 to 127 with two reserved exponents, minus 127 and 128 for special cases. So that is the complete representation of the exponent part in 32-bit format. Any questions from here?
স্যার যদি আমি 129 দিয়ে কোনো পাওয়া তাহলে ওটা কি নেবে না, মানে
You cannot represent 129.
মানে আমি ধরুন 2 to the power 129 দিয়ে দিলাম, তখন কি নেবে না ওটা?
No, not possible. It will give you an error.
মানে সেক্ষেত্রে 64 বিটে আমাদের শিফট করতে হবে।
You have to
আমারটা
go for
64। স্যার বলছি ধরুন আমি একটা মানে এক্সপোনেন্ট তো আমি 1.5 2.5 ও দিতে পারি, তো ওই
No.
না এক্সপোনেন্টটাকে
Exponents are always integers.
কিন্তু স্যার রিয়েল লাইফে তো আমরা ইউজ করি 2 to the power 1.5।
Yes. That is possible. You are talking about real world. What we are talking here is the representation in computers.
তাহলে
In
স্যার আমি যদি
computer representation, it has to be in this exponent has to be in terms of an integer.
so then how we calculate sir 2 to the power 2.5 or something?
হ্যাঁ স্যার, মানে আমরা তো ক্যালকুলেটরে তো এরকম ইনপুট দিয়েই থাকি।
Yes, of course, but there are special ways to handle that. Okay,
Oh.
this is the basic format. Of
Okay,
course,
okay.
There are other ways of handling such things. Okay. So let's move forward from this. Now, what can be the largest number that we represent in this single precision format? Remember that we are going for a normalized representation here. That implies that the most significant bit is always 1. And all the 23 bits are used for the fractional part of the mantissa. So basically, although this is 23 bits long, the mantissa is actually 24 bits long, of which 23 are stored in memory and one of them is implied or hidden. That is the most significant bit. Remember that expression that was shown previously in one of the slides that you can use to get a value for the number represented through this format. So let's see what can be the largest number. The largest number obviously would be the mantissa would be having all ones. That is the largest maximum number that we can consider here for the mantissa. For the exponent, the largest that we can consider is again, of course, all ones, but we have saved the last bit, the last number in that range as a special case. So we can go only up to 7 ones followed by a 0. So if we consider this case, then we have something like this. We are considering a positive number, of course, so the sign bit is 0. Then the exponent would be having 7 ones followed by a 0, and the mantissa would be all ones. These are the fractional part of the mantissa. The implied part is also 1, the most significant bit. So we first calculate the fractional part of the mantissa. Quite easy really, we just go on adding up 2 to the power minus 1, 2 to the power minus 2, up to 2 to the power minus 3. Sorry, 2 to the power minus 23. Then we add the most significant bit, which is simply 1, because this is going to be 1 into 2 to the power 0. 2 to the power 0 is 1, so that has a 1 in the most significant bit. So that is the mantissa part. What about the exponent? This is 254. We take out the bias. We have 127. So the largest number is going to be minus 1 to the power 0 into 2 to the power 127. Then the complete mantissa. And it comes out to be around 3.403, approximately equal to 3.403 into 10 to the power 38. It's a quite large number. So that is the largest number that we can represent in 32-bit format. What about the smallest number? We'll come to the smallest number next. But before that, let me just say that if some number is higher than this value of 3.403 into 10 to the power 38. So if you want to represent a number higher than that through this format, it causes an error. This is known as an overflow error. So attempts to represent numbers larger than the permissible largest number causes an overflow error. Now let us look at the smallest number. What would be the mantissa in the smallest number?
All zeros.
All zeros. What about the exponent? It cannot be all zeros because that is reserved. So you will have a single 1. So the mantissa is all zeros. The exponent is 7 zeros followed by a single 1. We know how the calculation is carried out. First of all, the fractional part of the mantissa is 0 here because all the bits are represented by zeros. We have the significant bit as 1. So the mantissa value, decimal value of the mantissa would be 1. What about the exponent? The biased exponent is 1, of course. 7 zeros followed by 1 in binary corresponds to a value of 1 in decimal. The actual exponent would be found out by subtracting 127 from the value of 1 and gives us minus 126. So the smallest number would be calculated as minus 1 to the power 0 multiplied by 2 to the power minus 126 multiplied by 1 plus 0. And approximately it comes out to be 1.175 into 10 to the power minus 38. Again, a very, very small number can be represented. If you attempt to represent numbers which are smaller than this number, then it causes an underflow error. We have seen the overflow error previously. Here, there is a case of underflow error if you want to represent or try to represent any numbers which are smaller than the smallest permissible number. Okay, let us have a look at this real number line with 0 in the middle. We have the largest possible number, 3.403 into 10 to the power 38. I have denoted it as max plus. It's a positive number, of course. So this is max plus. The smallest number, positive smallest number, is represented as mean plus, and it is shown by the red line, red vertical line on this real axis. All these positive numbers would be represented. Is that correct?
Yes, sir.
All the positive numbers in between
Max and
minimum
min.
positive and maximum positive can be represented.
Yes, sir.
Is it? This is not a continuous representation, by the way. The real number axis is continuous. Here, you do not have continuous representations. What you will have here are discrete representations like this.
একটা মানে অনেক মানে পয়েন্টের ডেসিমালের পরে অনেক দূর যেহেতু স্যার একটা জায়গায় তো থামবেই স্যার
মানে এখানটা সব রেশনাল ভ্যালুগুলো আমরা পাবো না, এটাই তো স্যার।
All rational values cannot be obtained. And that is the underlying cause why this round of error occurs. This is a discrete series. And it is not uniformly distributed, of course. There, the gap will be much sparser. Sorry, here it will be much more denser. Here it is going to be sparse. The same thing is mirrored in the negative direction also. You have the negative largest number, the negative smallest number, and the negative numbers, obviously discrete numbers in this range, would be represented. Positive infinity is to this side, negative infinity is to this side. Now, can you identify the overflow zone? Any number in these regions would cause an overflow error because it is larger than the largest number possible to be represented through this single precision format. Same thing happens in the negative direction as well. Where is the underflow zone? There. We go very close to 0 because 1.175 into 10 to the power minus 38 is very, very close to 0. But we cannot exactly represent 0. So that band on both sides of 0 gives us an underflow error. So here we have seen that we can go very close up to 0, but not 0. So how do we represent 0 in this format? This possible range of numbers, starting with very small 1.175 into 10 to the power minus 38 and going up to very large 3.403 into 10 to the power 38, this range does not contain 0 or even the infinities. In the course of calculations, it is quite conceivable that you come across a 0 value. So how do you represent the 0 in 32-bit format? This is where those special exponents that were reserved comes into play. In normalized form, of course, the mantissa has an implied 1. So the most significant bit to the left of the virtual binary point is 1. So even if you put all the mantissa bits as 0, the value you obtain is 1.000 like that. So it is quite impossible to represent 0 using this format. That is why that special place or special exponent were reserved to indicate 0. So what do we do here? All zeros in the exponent and all zeros in the mantissa. That would
ক্যালকুলেট করলে তো এক আসবে না মানে
that is why if you calculate this, it will not give you 0.
Yes, sir.
It is going to give you a finite value. But in this representation, it is forcibly mandated that if all the exponents are 0 and if all the mantissa are 0, that represents 0. And all 0 exponent as a result is not allowed anywhere else for any other number to avoid this confusion. That is why that particular exponent was reserved. Now here again comes the problem of positive 0 and negative 0. Depending on the sign bit, whether it's 0 or 1, we have two different representations of 0, positive 0 and negative 0. Although they have distinct representations, they are assumed to be equal, and it is considered that there is no difference between them. So the positive 0 is like this, all zeros throughout, and the negative 0 is sign bit having 1 and then all zeros. As I said, if you calculate this out, you are not going to get a 0 value. You are going to get a finite value in decimal representation. But that is not considered. It is mandated that if all the exponent and all the mantissa are 0, then it represents 0 in single precision format. Now what about infinity? In case of infinity, all the exponents is taken as 1. The sign bit could again be 0 or 1, and depending on that, it indicates positive infinity or negative infinity. So this is the representation of positive infinity, and this is the representation of negative infinity. And again, exponent of all ones is not allowed anywhere else. That is reserved.
স্যার 0 প্লাস পাচ্ছি 0 মাইনাস পাচ্ছি মানে এক্সাক্ট জিরোটা কি করে রিপ্রেজেন্ট হবে
Plus 0 is taken as equal to 0. Minus 0 is also taken as equal to 0.
ওকে স্যার
This is given in the standards. So as I said, even if you calculate it out, you do not get a 0 value. But the standard says that 0 should be represented like this. Now there are certain other special numbers as well. These are known as not a number. How do we get not a number? In short, they are called NaN, N small a n, not a number. Now, during the course of mathematical operations, you may obtain something which is not mathematically defined. 0 by 0 division, negative value under square root, these sort of things, they are not mathematically defined. You cannot write a value for 0 by 0. Mathematical value, numerical value is not available. To take care of these situations, this not a number representation is constituted. There are two different types of NaN representations. One is called QNaN or quite NaN. These quite NaNs or QNaNs do not give any kind of error messages. So the calculations are carried forward. QNaNs are normally carried over in computations. Examples of such QNaNs are again 0 by 0, root over minus 1, infinity minus infinity. These things are part of QNaN. So if due to calculations somewhere you get 0 by 0, then in the results window, output window, you will get a notation of NaN. But there will not be any kind of error messages. So this is how QNaN is represented. Depends on the sign, whether you have a 0 or 1 in the sign bit. Exponents are all ones, and there would be a 0 in the leading bit of the mantissa, and at least 1 in the rest of the bits of the mantissa. There would be at least 1 1. There could be so many zeros over there, but a single 1 is required. So that represents a QNaN. The counterpart of this is the signaling NaN or SNaN as it is called. In this case, you obtain an error message and the computations are stopped. In QNaN, computations are carried over. Even if you get 0 by 0, it does not stop. It goes forward. However, for SNaN, there is an error message and the computations are stopped. When does this happen? When there is no valid value in a variable. Say the variable is undefined. So then in that case, you get a signaling NaN error. If you try to use that variable in computations, you get that error. Overflow and underflow errors also fall under this signaling NaN part of it. How do we represent signaling NaN? 0 or 1 in the sign bit, depending depending on the sign, all ones in the exponent. Now here, the leading bit of the mantissa is equal to 1. Whatever happens after that is not a concern. Any string of zeros and ones could be present there. But only thing is that the leading bit needs to be 1. So that takes care of the single precision format. Now we come to the double precision format. As I said, here 64 bits are reserved for the representation with 1 sign bit, 11 exponent bits, and 52 bits for the mantissa. The bias value here is 1023. I think you can calculate this out by yourself, and you can also find out the largest number and the smallest number that can be represented through this double precision format. By the way, you can consider this as a sort of assignment for you, that you carry out these detailed calculations for getting these largest and smallest numbers. Do carry these out. Also, representation of 0, the infinities, positive and negative, and the nans are similar to 32-bit representation, and these are also left to you as a homework. You should carry them out. The final topic for today's class is called the machine epsilon. The machine epsilon is an indication of accuracy of a floating point representation. This is a measure of accuracy. How accurate is the representation? How do we define it? This is defined as the difference between 1 and the next larger number that can be stored in that format. So if we talk about 32-bit format, how do we represent 1 here? The representation of 1 is like this. The mantissa part would be all 0, because remember that we have that implied bit at the most significant position. So the mantissa part, when calculated in the form of a decimal value, would give us 1. The exponent comes out to be 127. We have the bias of 127. So if we subtract or deduct the bias from the biased exponent, we get a value of 0. So the number we have here is, of course, 1. The next thing is to look for the next larger number. What could be the next larger number here? There would be a change in the mantissa. What change? The last bit would be 1. There is the last bit. So this is the next higher number. You can say next larger number after 1. What is its value? The value would be something like this. Everything else is same. The exponent is again 127. That is the biased exponent is 127. So the exponent itself would be coming out as 0. Only thing that changes is that in the fractional part of the mantissa, the last bit would have 1, and that corresponds to a value of 2 to the power minus 23. So the number we can represent, the next higher number after 1 is 1 plus 2 to the power minus 23. So what is the difference with 1? The difference with 1 is 2 to the power minus 23. That gives us an approximate value of 1.19 into 10 to the power minus 7. It also indicates that we get an accuracy of decimal numbers of 7 digits in this format. That means after the point, you have 7 digits accurately represented. Now, what about the 64-bit format? 64-bit format would have a machine epsilon of equal to 2 to the power minus 52. Now, it simply can be calculated as 2 to the power negative power of the number of bits for the mantissa. And if you look at the calculations that we have carried out, it is quite clear that only thing that changes is the last bit of the mantissa. So the last bit of the mantissa in case of the 32-bit format is the 23rd place. In case of the 64-bit format, it is going to be the 52nd place. So if there are T number of bits used to store that mantissa, then the machine epsilon would be evidently equal to 2 to the power minus T. So for 64-bit format, we have 2 to the power minus 52, which is approximately equal to 2.2 into 10 to the power minus 16. That means we get an accuracy after the decimal point of up to 16 digits. Is accurate up to at least 16 digits. So obviously, if you require more precision, more accuracy, I should say, in your results, then you should go for 64-bit format. In the present days, all the computers that you get are mostly 64-bit formats. The architecture is 64 bits. Previously, we used to have, even 10 years, 12 years before, there were certain computers, even laptops, that had 32-bit format. And there was usually a problem regarding the softwares. Softwares for 32-bit format would not run on the 64-bit format. So there was a compatibility issue. But now, all the machines are usually 64-bit format. And in case of 64-bit architecture, this is known as double precision, of course, you get accuracy up to 16 digits after the decimal point. So that brings us to the end of today's discussions. Thank you. Okay, so questions?
তাহলে আমি যখন ইন্টিজার সেভ করব তখন তো মানে সব সময় ম্যান্টিসা পার্টগুলো সব জিরোই হবে তো, আর এক্সপোনেন্টটা অবভিয়াসলি 125 থেকে বড় হবে।
Yes, sir. That depends on the number itself.
স্যার আপনি বললেন যে আমরা মানে সমস্ত কন্টিনিউয়াস ভ্যালুগুলো পাই না ওই রেঞ্জের মধ্যে, তো স্যার মানে আমরা যখন এরকম এমনি নরমালি যখন কোনো কিছু একটা র্যান্ডম নাম্বার যখন রিপ্রেজেন্ট করি ওই ফরম্যাটে, মানে ওই যে এর মধ্যে যদি না পড়ে তাহলে সেটা রিপ্রেজেন্ট হয় কি করে, মানে তার জন্য কি আলাদা কোনো টেকনিক আছে, ইউজ করা হয়?
No, if you write a number which is not exactly representable, there is going to be chopping. তোমার নাম্বারের একটা পার্ট ওখান থেকে ছেটে বাদ হয়ে যাবে, তারপরে যে নাম্বারটুকু পড়ে থাকবে সেইটা হচ্ছে ওই রেঞ্জে কোথায় ফিট হচ্ছে সেই অনুযায়ী তুমি সেই নাম্বারটা রিপ্রেজেন্ট করতে পারবে। এবং সেই কারণেই হচ্ছে তুমি যে নাম্বারটা রিপ্রেজেন্ট করতে চাইছিলে সেটার সাথে তোমার কম্পিউটার রিপ্রেজেন্টেশনের মধ্যে একটা ডিফারেন্স থেকে যাবে। And that is why this round of errors means they are propagating. Consider this case. You want to represent 1/3. Very simple example, 0.333 recurring. You add 1/3 plus 1/3 plus 1/3. We know obviously it is 1, but if it is not going to give as 1, it is going to give something like 0.9999 like that. But of course, today's machines, even your calculators, they have a way around these things. There are ways of representing them in such a way that the representation is much more accurate. But of course, we cannot go into those discussions at this moment. But obviously, there are representations. There are also standards for decimal number representations in computers. Maybe I can circulate a note on that, on everything that we have discussed in today's class, and obviously there would be some extra material in that also. It's a note not made by me. It's available in the internet. It's an article written by Professor Rajaraman, V. Rajaraman, whose book I previously suggested to you regarding the computer representation or computer implementation of different algorithms. I will share that note also with you. You can read through that. I would not say it's compulsory reading, but you can, if you are interested, you can go through that. Okay, so let's take the attendance and then I will let you go. Just quickly tell me who of you are present here.
Sir,